This is my video report for Lab 3 magnetic field of a bar magnet. So a quick overview of this video report. I'll introduce the experiment and relevant physics principles, the calculations and code for the experiment, and then conclude with further questions. So the goal of this lab report was to examine the relationship between distance and relative position and the magnetic field of a bar magnet to further understanding of the Biot-Savart Law and the distance-dependence relationship with magnetic field. A quick overview of the experiment. I determined which direction was north on a bar magnet and then defined a scale which was perpendicular to that direction. I located my phone's magnetometer chip and labeled it with X, seen in the diagram, and then using that point varied the position of the phone to record magnetic field data at various locations. Jumping ahead, my results were field distance. For the field distance relationship was a value of n equals negative 2.8356 and a magnetic dipole moment at 3.28 joules per Tesla. So some important underlying physics principles in this lab include magnetic polarity, or magnetic field lines point from the North Pole to the South Pole. Also the Biot-Savart Law, which states that the magnetic field is inversely proportional to the distance between a magnet and an observation point cubed. The distance dependence equations on the right show the magnetic field from the bar magnet is proportional to a constant k times the distance to a certain power. So going into a little more detail with the experiment setup, I located my phone's magnetometer by looking at the x and y components for magnetic field as position varied. And then after marking this location, I measured the locations where the x component of magnetic field equaled varying amounts and recorded these values. My data for the distances is shown here. You can pause to take a closer look at it. The important finding here is the y-intercept, or L and K, in the equation I showed earlier, and the slope of the graph pictured, or the slope of the line, n. So we can use these values to calculate the magnetic dipole of the bar magnet by setting the magnetic field equal to kr to the n. This mu value comes out to be 3.28 times 3.28 joules per Tesla. You can pause to see these calculations. My glow script code provides a good visualization of this experiment. I created a function for the magnetic field and designated various locations, including on axis and 45 degrees off axis. The arrows pictured here represent magnetic field lines, where the magenta one in the top right is the off-axis point. Now I'll conclude with some further extension questions. If I hadn't oriented my experiment to compensate for magnetic north of Earth, and had laid out my rulers at some intermediate angle with respect to Earth's magnetic field, then the initial value for magnetic field wouldn't have been zeroed, and the data would have failed to account for this initial non-zero value. So, and then if I were to stick two identical magnets together and run the experiment again, I'd expect the values for the magnetic field to increase since there'd be greater magnetic force.